Now today we are going to continue the fundamental of theorem of calculus, and we're going to do part 2 of the theorem, which is called the evaluation theorem on page 555. If f is continuous over the interval a to b, as it always is in this chapter, and big F is an antiderivative of small f, then the evaluation, if you integrate as little f from a to b, that is simply equal to big FB minus big FA. Now let me write that down. The integral from a to b, that's the interval we are interested in, is equal to small f dx. I mean, the integral of small f is equal to big F at b minus big F at a. Now, whereas the big F is the antiderivative, any antiderivative. Okay, so now that looks like a simple formula, and it is, but it's not so easy usually when you evaluate it, because you have to do a lot of evaluation, which is grunt work, right? So the evaluation theorem, as the name implies, when you evaluate, you got to do a lot of, basic algebra. But that cannot be avoided, and that will be part of the homework, where you'll be doing a lot of evaluations. The difficult part actually is to come up with the antiderivative. If the antiderivative is obvious, that is, if little f happens to be the derivative of something else that you can see right away, then it goes pretty well. If you cannot see it, then life gets much harder. But we are going to learn different tricks to figure out what the antiderivative might be. And a lot of times we can find it. So in the meantime, however, we need to prove the evaluation theorem. So let's look at how it's proved. To prove it, then let's look at the next page, where first we are going to design a regular partition. That is, for a to b, we're going to get a bunch of x's from that xi is a regular partition. Remember what a partition is. A partition is where you have a and b, you pick a bunch of points, equal distance n points, or something like that, where you go from x1 all the way to xi, and whereas b is equal to xn, okay? Whereas a is called x0, and so on. And you slice it. In other words, we're slicing it to do the Riemann sum in order to calculate the area under the curve. So that's the partition. So we slice from a to b, we design a bunch of partition by dividing it into n equal parts. And then, so then we will do this. Then f of b minus f of a, okay, that's the big F, is equal to, first it equals to f of b. B is x to the power n, the last partition point. And then minus f of x is 0, which is so far so good. And then we're going to do this. We're going to write a whole bunch of stuff that equals to f of xn minus f of xn minus 1. That's the first piece, okay? And then plus f of xn minus 1 minus f of xn minus 2. So you notice what this is. The whole distance is, what we're doing is we do fxn, we minus xn minus 1, then we add xn minus 1 again. That's the second chunk. Then minus xn minus 2, and then we continue doing that until you finally get to the last one, which is f of x1 minus f of x0. So we're subtracting and adding the same thing all the way through in order to calculate each chunk. So this is the first part, and then the second. See, each one is subtracted. We add and subtract the same thing all the way through, so we could create we're basically building the Riemann sum. Okay, and so that's equal to that, and then next that would be equal. We'll use the summation symbol to mean that equals to I equals to 1 to n f of xi minus f of x I minus 1. All right, so that would be, if you were to add that up, that's what that is. So notice that each one is being canceled out. Okay, and we're doing this, we're basically making the formula more complicated. It used to be just fb minus fa, but now we get all the stuff happening. And why are we doing this? The purpose of doing this is so that we can construct the Riemann sum, and once we build that, then we can slap on the proof. Okay, so far so good. And next, what we're going to do is we're going to slap on something called the mean value theorem. Now, to review the mean value theorem, I will show it to you because I have it right here. And since I have it, you might as well stare at it. Okay, the one at the bottom. Now, to remember, the mean value theorem is such that the derivative, that is the average of the function at the bottom here, right? The average of a function, that is fb minus f of a over b minus a, is equal to the derivative of some point between a and b. So we'll use that. Continuing, so then to apply the mean value theorem to just one of these things, we have f of, we'll write this down. So f of xi minus f of xi minus 1. Okay, any one of these things by the mean value theorem is equal to the derivative of the big F, which is small f, okay, of c times delta x, where delta x is xi minus xi minus 1. So next, we are going to do, sorry, I jumped a step. First, we should say by the mean value theorem, this is equal to the big F, derivative of the big F. Okay, that is what the big F, and then delta x is xi minus xi minus 1. By applying the mean value theorem. And what is c? C is dependent on I, which xi we're talking about, is some point in between, according to the mean value theorem, times xi minus xi minus 1. That's what delta x is. Okay, to remind you what delta x is, delta x is xi minus xi minus 1. We call it delta x. It's one variable that has two symbols. So next we have, and what is big F? Big F, f prime of ci, is the same as small f. The derivative of big F is the same as small f. How do we know that? It's by the fundamental value theorem, right? So that equals the little f ci delta x. And now that's the fundamental theorem part 1. Okay, the derivative of big F is equal to the little f. Or is that, wait a second, let me make sure I say this right. Sorry, the big F is, the definition of the big F is that it's the antiderivative. In other words, it's given. We're not dependent, this proof does not depend on part 1 of the fundamental theorem of calculus. It just, yeah, so the derivative of big F is equal to little f as given, okay, as, right, because it says big F is in any antiderivative of little f, so big F's derivative is little f as given. So we are at this point, which is good. So the next step we have is then going back to what we did earlier, then f of b minus f of a is equal to this sum. Okay, so we'll rewrite that as f of b minus f of a, big F, of b minus big F of a equals to this summation of stuff that we did earlier, which is which we can plug this into this term, okay, which is the summation of f of ci delta x, where I goes from wherever it goes, 1 to n. All right, now so far so good. So now we have the Riemann sum. Now we're gonna let n goes to infinity. Okay, as n goes to infinity on both sides, this side doesn't change because this side is just two fixed values. This side goes to what? Then this side will goes to the it becomes the definition of so finally this equals to as n equals infinity, by definition of the Riemann sum for integrals, definite integrals, this side equals to from a to b little f dx. All right, and that concludes the proof. Now, when you look at this stuff, you can see that this goes back to the definition of the function, and specifically, this proof doesn't depend on part A. I mean, part 1 of the fundamental theorem of calculus. It stands on its own, basically. Now, there is, however, a way, an obvious way of proving the evaluation theorem. That does depend. If you use part 1, what happens is then you get around a lot of the grunt work. So as a result, if you use part 1, then this actually comes out faster. So I'm gonna assign the homework to you to prove the evaluation theorem with the help of part 1. Okay, and then afterwards, when you're done with the homework, then I will discuss it. It's something that that I thought was pretty obvious when I first saw it, especially after I did example 5.19. It sort of gave me an idea, even though that 5.19 has nothing to do with proving anything. So please, as a homework, please prove the evaluation theorem based on part 2. I mean, which is the part 2, based on the part 1 of the fundamental theorem of calculus. All right, so having said that, let me erase the board and we'll go to the next thing. Let's look at example 5.20 on page 556. We are supposed to calculate and use the newly learned evaluation theorem to evaluate something that's the integral of from minus 2 to 2 of a simple quadratic function t squared minus 4. Now to do that, first we are going to remember the formula for writing the integral. So to do that, we have, the formula of finding the antiderivative of something like this. Now to integrate t squared over 4, the antiderivative, there's a formula for that, for just t squared. Okay, for just t squared, what you do is you raise the power, you add 1 to by the power, raise the power by 1, and then divide it by the power. Okay, so that would be the n. And then, well, what you do is actually, that's just for t squared. What about 4? Well, the 4 is done a different way. When you integrate a constant, then you just try to remember what becomes the constant is just t. So when you integrate it, then you have, say, what's on the top line, okay? T squared becomes t cubed because you raise the power by 1, okay, and then divide it by the power, which is 3, and then minus a constant, you just add think about taking derivative of what becomes a constant. Well, just x, okay, in this case is t, so the antiderivative of minus 4 is just minus 4t. And then, okay, so that's the integration part, which is quite easy for this particular example. And then here comes the tedious part. Now you have to plug in the value of t from 2 at 2, and then subtract it at minus 2. Okay, and then hope not to make a mistake through all that subtraction and a ton of negative signs and stuff. And if you don't make a mistake, then you eventually come up with some answer. So please do the example 5.21 as homework. Next, let's look at example 5.21. The same thing. You are integrating something, and you're going to use the power rule. Okay. Now this looks like a fraction, but it really isn't. It's just that you're going to split this fraction into two fractions and then turn it into a power rule situation, as is shown on the next page. Okay. It's simply you just split it into two fractions and then break it up and integrate each one by the power rule. And the power rule is raise the power by 1 and then divide by that new power. And then you have to, once you have done that, you come up with a bunch of fractions, like this. And then you have to evaluate x value at 9 and then subtract it by the same thing at 1. Let's see. See the second line here? You just plug in, first you plug in 9 in the first part, right? And then you plug in 1 at the second part, which is a lot of work, so I'm going to let you do that, which is example 5.21. Now, I know that's quite a bit of grunt work, but for the evaluation theorem, there is no getting out of doing some grunt work like that. And just make sure that you do your subtractions and the negative signs and keep it all straight, and not get a single sign wrong, because if you do, then you're going to be in for it. Okay, so next there is example 5.22 is the same thing. Okay, you're going to integrate something and then you're going to plug in some evaluations. So I will let you do that. Please do 5.22 as well as part of your homework. So for homework, please, which is on page 562, please do problems 171, 175, 79, 83, 85. Now notice that problem 185 has a slight typo. It's supposed to read tangent theta d theta. And my copy is missing something, missing a theta in there, but you know what it means. It means tangent theta, not just tangent. Tangent what, right? So, and anyway, so yeah, that's 185, 87, 89, 91, 93, 97, 201, and 203, part B, only part B. Part A asks you to derive a formula for some ellipse, and we're just going to skip that, okay? We're just here to do integration, not working with ellipses at this moment. So, so you just assume part A is the formula provided in part A is true, and use it to do part B. And that will be the end of this, all the homework. Now, so please go do your homework, and when you come back in this video, I will go over some of the homework, and more importantly, I will do the proof for the evaluation theorem, a second proof that is dependent on the part 1 of the fundamental theorem of calculus. So now that you have finished your homework, let's first I want to do the evaluation theorem. Is a different proof, a proof that I came up with, and that I think that is much simpler. But there's the condition, however, it is that it does depend on part 1 of the fundamental theorem of calculus. So you might think, why do we have to see two different proofs of the evaluation theorem? It's just for the fun of it, especially because my proof is shorter, so it's kind of interesting to do. And anyway, so let's look at the proof the evaluation theorem. Okay. So first, let's figure out what the evaluation theorem says. Going back to it. Now going back to the evaluation theorem, which is on page 555, it says that if f is continuous, small f is continuous, and big F is any antiderivative of small f, then, so we have a small f, which is continuous. So so here's what's given. Big F is the antiderivative of small f, a antiderivative, doesn't matter which one, because they're all they are within the constant of each other. So anyway, big F is antiderivative of small f. In that case, then we're supposed to prove OVE, prove that the integral from a to b of small f is equal to the evaluation big F evaluated at b minus big F evaluated at a. All right. So here's how I proved it with taking advantage of the fundamental theorem of calculus part 1. So here's what I did. Now here's the proof. Okay. Now I'll write down proof here. Let g, well, come up with some function called g of x. Okay, g of x is equal to, I'll define g of x this way, equals from a to x f of t dt. That is the definition used in the fundamental theorem of calculus part 1. Okay, then by part 1, part 1 states that if that is true, then g prime of x is going to be equal to little f, right? That's just what the part 1 says. Okay, now here's where I use the part 1. And then next, I'm going to say, now then we'll choose the f of x as given is an antiderivative, right? Then in that case, that means what? That means g of x is going to be equal to f of x plus some constant. Because all antiderivatives, this is an antiderivative, that's an antiderivative, all antiderivatives are within the constant of each other. And that by that I'm quoting corollary 2, which I will show it to you here, being that I have it on this cute little picture. Right? Corollary 2 is proved in chapter 4. I have copied and pasted here, where it says if f and g have the same derivative the whole time, then f and g are within a constant of each other. All right. So then see, f prime and g prime are the same function. That means it's that is big G and big F. Then they must be within a constant of each other. Okay, so having said that, let me dig out my notebook. Continuing, then next we're going to calculate what is g of a. G of a, notice g of x is defined this way. So if g of a is plug a up here, when you integrate from a to a, that's the area under the curve going from a to a. That just, there's no space, you're not moving. So there's a rule that says if you integrate from this to the same spot, the answer is 0. So g of a equals to 0. All right. So that means you will plug g of a into this equation. That means what? So f of a, that means f of a plus that constant equal to 0, which means f of a equals to the negative constant. Okay, negative c. Where's my negative? There it is. Okay, f of a is equal to negative c, or put it another way is c equals to minus a. That's probably better. C equal to minus f of a. Okay. And then, so here we have come to the end. Let's write this thing down. Okay, so the integral of a to b f of x equals to, well, that's what we're trying to prove. So I'll write it down here. Integral f of x dx. I'm missing my little dx here. There. F of x dx is equal to, we'll plug it into this thing, equals to g of b, right? By this formula. That equals to g of b, because that's how I define g of x. So you plug in b, that would be this integral. Well, this one's t, and let's see, does that matter? Sorry, the variable here should be t. all right, because I defined it as t, so let's stick with it and not cause any confusion. So f of t dt, that's g of b, all right, I just plugged this thing in here, which equals to g of b equals to, following this formula, okay, g of b equals to f of b plus the constant. And whereas what is the constant? The constant equals to negative f of a, f of b minus f of a. And that finishes my proof. Now you might say, but that's that's an x there, whereas I have a t here. Well, it doesn't matter, okay? That this is called a dummy, as your book puts it. The dummy variable, we don't care what it is. The purpose of this is simply saying that, let me move over. The purpose of this is simply saying we're calculating the area of the function f from a to b, and that's what this says too. So you can change the variable inside, and it doesn't make any difference. And my point is that is my proof, and it seems to be somewhat shorter. Not that the other way is really that long, but this seems somewhat quicker than than the version that the book offered. The reason it's shorter is because I'm using the part 1, which did all the heavy lifting basically, which is why this seems easier. So anyway, so let's having said that, let's look at some of the homework that I want to do. Now, while my proof might be shorter, so it's beneficial that way, the original proof does have the benefit of going from the ground up, being that it doesn't depend on part 1, so that it shows you exactly why this is the case. So both proof has its advantages and disadvantages, and I just want to show you this one too for the fun of it. So let's look at the problems. Now the homework for this section is still fairly straightforward because you're not doing any difficult integration, that is the finding of antiderivative yet. So you mostly follow the rules and then figure out what the antiderivative is. The one part that's helpful for the homework is looking at the integral chart, which is on page 489, which I have also I have written down under the video. So let's look at some of the problems. Okay, problem 175. I will talk about it briefly. Okay, briefly on my notes. Is that too bright? Anyway, so problem 175 says that you have to integrate x to the power 99. Well, you just that follows the power rule, which says you raise it by 1 and divide by that power. So 99 goes to 100, divided by 100, evaluate it from 1 to 0, and that's just 1 over 100. So a quick and easy problem. Problem 185, a similar story. You are supposed to integrate secant tangent, secant theta, tangent theta. Well, to do that, you have to look up the chart, which tells you the derivative of secant is equal to secant tangent. And so you pull secant out of there and then evaluate it from 0 to pi over 2, which end up being square root 2 minus 1. Next problem, what is that? Oh, problem 191. You integrate from 1 to x of e to the power t. Well, the antiderivative of e is just e, right? So it becomes e to the x minus e to the 1, e to the power 1. And I believe that's the right answer. And then finally, problem 100, and what is that? I can barely see it, it's too bright. Let me reduce the brightness a little bit. Come on, go down. Okay, see if that's better. Now, the last problem is 193, which you integrate the sine of t. Now, this one, of course, it becomes negative cosine t, but by the time you calculate the whole thing out, it equals to 0. That means the antiderivative f of x is the constant function. Okay, f of x equal to 0 the whole time. In other words, it's the line on the x-axis. Okay, that's 193. And the last problem I want to talk about is, I think I flipped the wrong thing. Okay, the last problem I want to talk about is problem 203, part B. And I would like you to just assume part A. Oh, great, I lost that page again. Okay, I found it. Now, that which asks you to calculate some kind of area. Okay, now the area, oh, no, sorry, some kind of average distance. The distance is given in part 1 as this particular formula, which I will. The distance by part A has been calculated to be represented by the formula d theta equals to d theta equals a plus cosine theta. Okay, this is problem 203. Now, if in that case the book asks you the average distance, the average value is defined as this. From, what is this? From A to B. In this case, theta goes from 0 to 2 pi. That goes through the entire ellipse. So theta is 0 to 2 pi. The average is b minus a, which is 2 pi minus 0. The formula for the average is printed in a different part of your book, which is just this one. It is 1 over b minus a, integrating from a to b, f of x dx, the definite integral. Okay, it's defined, I don't know, a couple of sections ago, or maybe last chapter, I don't remember. The point is, so that is the average. So to calculate the average, you stick this formula in here, a plus cosine theta d theta, and then you calculate this this thing, which if you were to calculate it, you come up with something like this: 2 pi. We will integrate this. Okay, that is this is a plus, which means that it will eventually equals to a times 2 pi for this part, and then plus is there a c in here? Yes, there's a c in here. C cosine theta. Okay, plus c times the antiderivative of cosine is the sine, so c sine theta, and then you are evaluating it from 0 to 2 pi. Now from 0 to 2 pi, this value will be 0, because sine of 0 is 0, sine of 2 pi is 0. So the answer is just A. And that should be the right answer. Now I should draw this parentheses right here, because being that this is a constant, the value is just a times 2 pi. So the evaluation, it only includes this part. So and then and that's why. But this thing is all multiplied by the 1 over 2 pi. So then that's why the answer eventually is A. All right.